So this is how we solve question 3. We are given a schematic whereby we are having a representation of a beam that is carrying a weight that is it is varying. So it is not an uniform load, it is varying. So we call this trapezoidal trapezoidal load, or can say it is a uniformly varying load, but you can also decompose this one to have uniformly distributed load, that is up to here. Then we have uniformly varying load, that is the triangular load, this part, as you can see here. So first I went ahead and found because we started to solve a real life problem, I went ahead and found the self-weight of the beam, because the beam is a concrete beam, so it is supposed to have its own weight, and it has to carry itself. Okay, so when the beam is carrying itself, it normally, because it has a uniform cross section whereby we have B H, the base and height is uniform all through, up to from the beginning to the end. So we have a uniformly distributed load like that. Okay, and now we add the load that is on top of it. Okay, so how did I go about it? I assumed that the beam dimensions B times H, that is the base given by 200 millimeters, and H is 300 millimeters. Okay, and the total load that is carried by the beam is equal to the self weight of the beam plus the applied load. Okay, the applied load, that it is the load that we can see on top of it. Okay, so how do you calculate the self weight of the beam? The self weight of the beam is equal to unit weight of concrete times the cross section area. Okay, the unit weight of concrete is given by is a known value, which is 25 kilonewton per meter cubic. So the self weight is given by, you take because it's in meters, convert also the other dimensions into be in meters. Okay, divided by 1,000. So millimeter divided by 1,000. Okay, so we're going to get this one. So it is going to be 1.5 all through. Okay, so now we apply the combined load to draw our FBD. FBD is the free body diagram. So what does the FBD require us to do? We need to show the support reactions and the load that is being carried by our beam. Okay, this one is, we are given as 200 newtons per meter, so I converted it to kilonewtons so that it can match with the beam self weight in kilonewtons. Okay, so we are working with kilonewtons. Here we are told here this is the roller support, and we know a roller support has only a vertical reaction area y, so we do not have a horizontal reaction. But for a paint support, we have both vertical and horizontal reaction. We have reaction along a vertical reaction and a horizontal reaction. For ease of calculation, we divide the load into 3 areas and identify where they are acting on the beam. Alright, so because we already know the dimension here is 3 meter and here 3 meter, so the total length is 6 meters. Okay, so I've come here and now I have simplified by getting different shapes of our loads. Okay, so because those shapes are going to help us calculate the total load that is acting on the beam, and it will help us find the moments. And now we're saying to find the moment, we need to know exactly where the maximum load under each area is acting. Right? And the moment is given by area times centroid of the area. Okay, so what is a centroid? a centroid is like a center of an area, right? We can have a regular shape and we can have a irregular shape. So for regular shapes, we have a rectangular shape. You can get the centroid of this area, which is basically it is at the center of it, so it is L over 2. Okay. And because L is 6, we get the centroid of 1 is 3. So this is area 1, area 2, area 3. Area 2 is also it's a rectangle, but because we are finding the centroid from this point, because we are going to find the maximum at point A. Okay, because the moment here, some moments here is 0. Okay, and also here it is 0. So we're going to find the moment from this point. So the centroid, the half of this is acting at this point. Okay, so it is here. So what is that dimension from here? It is this length over 2. Get now half of that. We are going to add now the distance from here up to here. So it is the distance from here all the way up to this point. So it is L1 plus L2 over 2. That is why you have seen here, I've said it is L1 from plus L2 over 2. So it's going to be 4.5 meters. Okay. The centroid of the third one from point A, it is now, it is also starting from this point, is this length up to here plus this point up to the centroid here, around here. Okay. And for a triangle, the centroid is found depending on the direction that you're coming from. If the direction is from the sharp end going this way, it is at 2 over 3 of this length. But if you're coming from this side here going this way, it would be 1 over 3 L. So 1 over 3 is going to be here. So 2 over 3 from here, that is where this distance is longer, 2 over 3. And this one is 1 over 3. That is why it is shorter, but it is coinciding. So that is why I've given you both the ways of finding the centroid. From point A is L1 plus 2 over 3, and from L, but they are all acting at the same point. If the total length is 6 meters, so the total length here is 6 meters. From this side, the centroid is acting at 5, and from this side, 5 here is 5 meters, and the total is 6 meters. So from point B, the centroid is acting 1 meter from here, so it is at the same point, exactly 1 point. That is what I was trying to show you here. It occurs at the same point. So we do not need this anyway. So we are going to find the moments acting about point A, and we get it to 0, okay? Because at point it is a roller support, and the moments that on a roller support is equal to 0. So we're going to take the area 1 multiplied by the centroid, each centroid. We add the area 2 multiplied by its centroid, because we have 3 shapes, so we have three forces. This one will give us the total force, this will give us a total force. So this is a length, and this is a force. So force times length is moment. Okay, so that is why we are having area. So moments, normally we say we take moments this way as negative, and that is going, if this is a point, the other moment that is going turning it this way, it is positive. Okay. So that is why we are having these negatives here and positive here. Okay. And if this one that is going in clockwise because the arm of the clock goes this direction, so that is why it is called clockwise. And those moments that are in clockwise direction are negative, and those that are in positive direction are anti-clockwise direction are positive. And this one does not stop here. For example, this one, the anti-clockwise, if it is acting at this point, about this point, so it's trying to turn this point this way, okay? And this negative moment, it is try to turn this point this direction, okay? So as long as if you are talking about point A here, for example, this is point A here, and if this is point A, this is point B, the reaction here is facing upward about this point, so it is trying to lift this point upward. So if it is trying to lift it upward, this direction is anti-clockwise, so that is why this one is positive here. And the other ones that are turning it down, that are the safe weight and the applied loads, are negative loads, all of them. Negative, 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 and positive. Only here positive. So when we substitute here, the area WL is basically, if it's uniformly distributed load is given by WL, is the same as taking the area of that shape. So WL times the centroid, WL times the centroid. And this one is a half BW because it's a triangular load times the centroid. And this one is RBY, the reaction times the distance that is acting. Because it's a point load, you are not going to use a centroid because it's a point load, it's a set reaction. So it is from this distance, 6 meters away from point A, 6 meters. That is why I have substituted everything the way it is here. And the only unknown here is RBY, so that is why we are trying to get the reaction at point B. So I found it as 5. When you simplify these, you're going to get these and these. So the answer is that. And to get now the reaction at the other reaction at AY, we're going to apply this equation here, the summation of forces in the y direction. Okay. So we've said here force is given by WL, and WL is basically the area. So this is WL. So safe weight 1.5 times 6 WL minus 3 WL. It is acting from halfway from that support. So this one does not matter. It is basically we are trying to convert that area load into a point load. That is what it basically means, because it's 1.5 kilonewton per meter, and this is meter. So this meter and this meter we cancel and we remain with kilonewton. So you have just converted that one, the area load, into a maximum point load. Is it minimum or maximum, whichever the way case. So when we multiply the UDL by the distance, we're going to get the point load of that UDL. This one times this is the length. This is the W times the length. This is half, because it's triangular, we are going to have the area, just the area times the weight. So what is the area? Half BH. Half BH. Okay. And the other reaction here, I forgot to include this one here. It is so this force is facing down, that is why it is negative. It is facing down the y-axis, it is pointing down. So we say the forces that are pointing down are negative, the forces that are pointing up are positive, as you can see here. So that is why we have negative at here, and we also have these forces, the reactions are facing up. So RBY is facing up. So we are summing every force, alright? Because we have the UDL acting here, and we have the reaction facing that direction, okay? the reaction facing. So we have these forces, so we are converting this one as to point loads, the UDL to point loads, like that. The other point load is acting here, and that for triangle is acting here. So we have this point load, facing down, and have this one facing up, okay? So that is why we have all these equations. So we are adding, we remain with one unknown, which is RAY. So when you the only unknown here is RAY. So when you solve for it, you are getting 4.75. And as you can see, we expected this RY to be smaller than RBY, because we can see that most of the load is acting past midpoint of this one. So we have this point is carrying more load than this point. So that is why RY is 4 and RBY is 5.5. That is what this note is saying here. Okay. Now, forces in the x direction. We only have one x direction here, because it's a pin support. A pin support has two reactions, vertical and horizontal. So how many forces are facing the x direction? Just one. So when we add this one, we are going to get 0. So RBX is 0. So just RBX is 0. Okay. So the required reactions are RAY. For the roller support is 4, and for the pin support is 5.5. Yeah, and that is just basically what we are required to solve for. Thank you.